Hey guys, this video is going to cover complex circuits, which are just combinations of series and parallel components that make up a circuit. So it has circuit elements of both the series, which means that the current in parts of resistors or circuit elements that are in series with each other, they all share the same current. The same current runs through all of them. But the same current does not run necessarily through parallel parts. So what we're going to do in this video is just take a look at how do you figure out what, say, the equivalent resistance or the total resistance is of a complex circuit based on the setup of the circuit. So let's get a picture in here so we can start to analyze this and learn some strategies. Alright, so here's a picture where we have several resistors. Let's just say they're light bulbs for now. And we have a battery power supply that's 9 volts. Okay, so take a look at the setup and then let's trace some paths like we always do. It's the first place to start to really understand what's going on. We're going to use conventional current. So remember, we're going to start at the place of high potential, the positive, and we're going to move through the circuit like this. Okay, so we pass through that resistor. Then we reach this point right here called a node or junction, which you should know from the parallel circuits. And let's say I decide to go down this path, and then at this junction, I cannot go to the right because that would be going to a place of higher potential against the electric field, which would require some sort of external work. So I'm going to go this way, pass through the R5, and then head back in that direction. Let's get a different color and trace an alternate path. If I hadn't stopped at that junction, I would have continued on and moved through the R4 branch and then continued back on. I cannot go up the R3, R2 branch because that would be going once again to a place of higher potential, which is not possible without external work. Continue on and head back. Okay, so you can see here that we have a very similar setup to what we had with the parallel circuit. Except now there's a few things to take into consideration. Let's first figure out where is the current the strongest. Alright? And you can see by the colors that the current is the strongest where the loops overlap, right? Because by conservation of charge and by conservation of matter, there's more in these regions, therefore there will be more current. Alright? So this region and this region have the most current. Alright, you can also include all this side over here. I'm just not including that. But all those regions have the most current. And then you can see where the purple and the blue split from each other, there's obviously less current in each of those individual branches. Okay, so let's play the little game where we eliminate resistors and see what happens. So if I eliminated R1 and I left a blank space there, what would happen in the circuit? Well, they should all go out, right? Because all of the currents have to pass through R1 to even reach the others. So if there is a blank spot, there will be no potential difference and therefore no movement of charge. Which other resistor would cause the same outcome? Hopefully you picked R5 for the same reason, right? If that gap is there, then the purple and the blue circuit, if you will, the purple and the blue loops, will both be interrupted. Choose one resistor to remove that would not affect any other resistors in terms of if they would go out or not function. Good, hopefully you picked R4 for that answer. That one is the only one that's in the blue loop by itself. Right? Now, R1 and R5 are also in the partial blue loop, right? So removing R1 or R5, like we said, would make all of them go out. But removing R4 would only make that back branch, this branch over here, right, would only make that back branch disappear. It wouldn't function anymore. So R2 and R3 would still be on because the purple part of the blue current and the blue and purple current, the purple part of that is still functional. Now, if I were to remove, let's say, the R2, alright, if I remove the R2, then the R3 would also go out, right? But the R4 would still stay lit, R1 and R5 would still stay on if these were light bulbs. Now, would the currents change through those light bulbs if any of these were eliminated? Yes. Even if they didn't go off, they would still have a changing current. And we're not going to talk about that right now. We're just trying to analyze what things are independent of each other, right? So R4 is the most independent piece of this whole circuit. R2 and R3 come next because they're dependent on each other, but I could get rid of them or one of them and still have R4, R1, and R5 function. The only ones that are completely integral to the circuit are R1 and R5. If you remove those, then everything would go out. All right, so now let's go and take a little bit more of an analytical approach to what's happening here. So I'm going to go to a new slide and clear up this picture. All right, so I have this circuit again. And what I want to do is I want to try to condense this down to one equivalent resistance. I want to know what is the total resistance. Now for series, we know that if you add more resistors, you just keep adding them normally, sort of algebraically, arithmetically, and you get an answer of resistance. And the more you add, the more resistance you have. We remember with parallel, adding a resistor, really what you're doing is adding branches, right, with resistors in. The more you add, the less the resistance gets because you're adding more options and therefore allowing more current to flow in the total. Here you're doing a combination of both, right? Choose two that share the same current. What two resistors share the same current? Take a second. If you need to pause the video, you can. Okay, hopefully you saw that R2 and R3 together share the same current. Okay, so they share the same current between the two of them. Whatever runs through R2 has to run through R3. Now, do they have the same voltage drop over each? Hopefully you would say no, because you can see that they have different resistances, so it would require a different voltage drop. Which other two? Are there any others that have the same current? In fact, it is R1 and R5, right? They share a current as well. Now, is it the same current as R2 and R3? No, that's not, because they're not in the same branch, but they'll have more here. But anything that gets to this point has to split, but then we'll come back together again to be what it was before. Conservation of charge, right? And so I'll end up with having R1 and R5 in series with each other, right? In series with each other means they have the same current running through them, okay? So R2 and R3 have the same current running through them. R1 and R5 have the same current running through them. And R4 has a different amount of current running through it, right? That one's kind of on its own. So we're going to look now at how we would go about actually calculating the amount of resistance. So I'm going to go ahead and erase what I have written here. Okay, and remember, if you can figure out which ones share the same current, then you can make it easier on yourself to answer the equivalent resistance question. Okay, so let's do this. I'm going to start by adding R2 plus R3 because I know those are combined together. So I'm going to do 3.3 plus 8.2, and that's going to give me 11.5, I think, if my math is correct. So doing this would be the equivalent of having one resistor there that's 11.5. So I'm going to do some little magic animation here to get that to go away. Okay, so instead what I'm going to have is, what I've essentially done is that I've just combined two to make an equivalent resistor. Because what I'm slowly trying to do here is combine all the resistances into one total resistance, right? Now, we can see that the current's going to go through R1, and still, same as before, it could do this, or it could go on the outside. Okay, so now 11.5 and the 4.7 on the outside, those are not in the same branch, but they are just parallel with each other. So what I'm going to do is I'm going to use that addition technique that we got before. I'm going to say 1 over R4 plus 1 over whatever that new one is, 11.5. So let's go ahead and put that in there to the negative first. So that's going to be 1 over 4.7 plus 1 over 11.5 to the negative first. So let's calculate what that is. And I come up with 3.3, I think, somewhere around there. Alright, so I'm going to do some deleting again so I can show you what we just did, right? We condensed this and this into one thing. Alright, so what basically happened was we did that, right? So I'm slowly condensing this down by breaking it up and combining parts. Now you can see you have a simple series circuit. So that's going to be 330 plus 3.3 plus 10. Now something that I ignored in this video was that some of these were kilo ohms, which is like 1,000 times an ohm, and some were not, like the 330. I'm just pretending that they're all in ohms just because I'm trying to teach you the concept. It doesn't matter about the addition. In this case, then I just add these three together, and I would get 330 plus 3.3 plus 10. That's going to be 343.3. And that's going to be the total. Alright, so that should hopefully help you, and then we're going to do one more, and I'll kind of show you once again how we condense these down. Alright, so here I have a different circuit. At first glance you may be freaked out. Just take a breath and trace the current. Now it has this weird looking battery. It's just an alternate symbol for a battery. You just start at the positive. Okay, I'm going to go here. We're going to go through the 3. Oh, we hit a node, and we can either go up and across, or we can go, let's do the other one. We can go down and across. Right? Then we could combine for a little short period, and then it's going to be able to split again. It can either go up here all the way back, or it can go down here and all the way back, or they could flip, right? You could have the purple go on the top for the second one and the green go on the bottom for the second. It doesn't really make a difference. There's just some current going through the top and some not. So you can hopefully see something here that might be helpful in condensing the circuit down. So let me erase these. And what I'm going to try to do here is I'm going to try to combine these two into one. Then I'll combine these two into one. And then it will just like be having three resistors in series. So I'm going to do for the one on the left, and let me try to resize this, kind of move this around. I have another picture under there, so I'm going to have to erase some of that. Okay, let's see what I can do here to kind of hide some of that. Alright, so I kind of hid some of that other stuff that was in the background. So let's do our little combination circuits here. So we're going to do 1 over 2 plus 1 over 7 to the negative first, because those are in parallel. That's going to give me a value. And then I'm going to do 1 over 4 plus 1 over 9 to the negative first, and that's going to give me a value. So let's calculate those. Alright, so there, I calculated those. So what we in essence did, and I kind of try to do it visually, is we erased that, and we erased this, and what we did in place of that is we found what are those two combined, and those two combined. So we have something that looks like this, and this one's 1.56, and this one's 2.77. Now it's easy, because now they're all just in a loop. And so I'm just going to add the 3, the 1.56, and the 2.77. I'm going to add those all together to get the total resistance of the circuit. And I get, let's see, 7.33, I think. Okay, ohms. So from that big picture that we started with, if you want to reverse the video and look at it again, we got to a condensed circuit that only has 7.33 ohms. Okay, it makes sense that that everything had to go through the 3 ohm resistor. So that's why it was added last in series, right? Because it shares the same current as the 1.56 and the 2.77. Now the 1.56 and the 2.77 aren't resistors that actually exist in reality, right? Because they're just combinations, they're equivalent resistors to what would be there, right? And so that current would split between the two. So it makes sense to say that if I combine the two, that it's sharing the same current as what was before it hit the junction. So I would recommend watching those two examples again to really try to get that into your mind. Let's just quickly look at how we'd find the total current, and hopefully that's very simple at this point, is that we take the delta V equals I times R that we derived and figured out, and then we'll put the delta V as 12, and then we need to put 7.33, I'm running out of room here, I. So we divide by 7.33 on both sides, and we should get 1.64 amps. Alright. So next and last but not least, let's look at what would happen if we were to remove bulbs, and that might help us kind of identify where the total current is flowing through. Okay, so I put the two pictures back here just so we can kind of look at a few things. If you kind of want to summarize what you have to do, I would say that the best thing to do is the first step would be to combine any resistors in the same branch. Alright, so let's look at which those would be. So I could combine those two, right? That's what I did first. And that's it, because those are the only two in the same branch, right? All the others kind of are in separating branches. On the second one on the bottom, there aren't any that are in the same branch. So then the next thing would be to combine branches until equivalent resistors, so I'm going to write it in the shorthand, until equivalent resistors are in the same branch again. So what I mean by that is I would combine the 2 and the 7 like I did before, and then I would combine the 4 and the 9 like I did before. Now those equivalent resistors, right, that one resistor is equivalent to the 2 and the 7 combined, and the other one resistor is equivalent to the 4 and the 9 combined, then I will be able to have the 3, and I think it was 1.56 and 2.77, now they're in the same branch again, and then I can go back to step 1 and combine any resistors in the same branch, and I just keep doing that over and over again. So the one on the top, just to look at it in this way, is I would combine the R2 and R3 according to the first rule there. Then I'd combine any branches. So I'd combine the R4 and whatever this equivalent was. Now I've got R1, R5, and there's this new big combined piece in the same branch again, and so I combine those resistors in the same branch. If you have noticed, step 1 is adding in series, because they're in the same branch, they share the same current, and step 2 is adding in parallel, doing the 1 over thing that we were doing that we derived in class. So hopefully that video kind of gives you a basic overview of what you have to do, and there's an accompanying worksheet that you can practice these with, and we will pick up again and in class and do some more analysis together. Practice makes perfect on the circuit analysis. If you have to practice. If you don't practice, you will really struggle because you have to make it second nature. So don't be afraid. just go through the rules, trace the current, and then follow these 2 summarized steps. Good luck, guys.